Okay, so for this video, we're going to work through an entire free response question, and the idea was that you have already worked this one through to the best of your ability, and I'm going to step-by-step it in terms of what you're being asked to do. And this one is really, really familiar, or should be, in terms of looking like those other questions that we had been focusing on. So this is looking at a separable differential, and it's got our two pieces being multiplied together. And then they're saying that we have an initial condition of f of 0 is 1. They've provided a slope field, again, a really, really aggressive slope field. And there's a couple features before we just pop into this thing that I want you to notice. When y equals 3, let me get a pen out here. When y equals 3, I don't like that one. If you put a y equals 3 value into the slope field, you're going to get 0 times the cosine of x. What happens then is you create this line or this band of 0 slopes. So those are all 0 slopes. It's also referred to as an equilibrium solution, which they're not referencing that specific term here, but we've encountered and seen that term before. That actually is going to come into play right at the end of this problem. And so it might be a small kind of thing that looks like a throwaway, but it's an important point to notice, and there's actually a reason they topped the graph out here and stopped it at 3, so that you could see that, and they're kind of foreshadowing or giving you a hint when we get to the bottom when we have to decide on a particular course of action. But we're not there yet, so just put that aside and just note that, hey, we're going to come back to this idea. What we're asked to do in part A is just, here's a slope field or a piece of the slope field, sketch a solution curve through the point 0, 1. So again, they're giving us an initial, so there's our 0, 1, and they're just asking you follow the slope field as best you can. So from there, it's going to come up and 0 out and come back down, and that's that cosine portion of things that's making it kind of look trig value-ish. And then we're going to pop down, flatten out, pop back up, and it's going to have an appearance similar to that. Now, is yours going to be exactly like mine? No, but it's got to have that rough shape. And if it does, you're good to go. And the solution, the print solution, is also up on the solution guide tab in the folder for these worksheets and documents. But I think it helps to actually see it being processed versus just the ultimate outcome. So that's the curve that's being sketched in. Second, they want us to write an equation for the tangent line solution in part A. Use the equation to approximate f of 0.2. Again, like we've seen in the past, for A and for B, they do not want us to actually figure it out. And in part C, you can see particular solution to the differential equation, that key phrase, that's when they want you to come up with a y equals. A and B, they don't. B, we're just coming up with an equation for the tangent line to the function, but we don't need to go to the length of actually finding the function. So they've given us 0, 1. Well, so in part B, I'll just put part B over here. That means y minus 1 equals m times x minus 0. That's the structure, and then we just need to go in there and get m. We've got an equation for slope. So our equation for slope is dy over dx equals 3 minus y times the cosine of x. And we have a point on the curve that they want us using, 0, 1. So we're going to say, okay, well, the slope or our derivative or our y prime or our dy dx, they all mean the same thing. If I take and plug a 1 in there, I've got 3 minus 1 for our y, or for our first part of the expression. And then I've got cosine of 0. So cosine of 0 is 1. 3 minus 1 is 2, so I have 2 times 1. That means that my slope is 2. So for my equation, I've got y minus 1 equals 2 times, and I'll just write x minus 0. That is technically correct. You're good to go. You don't need to do anything more with that. And if you want to leave it like that and then process the question, you can. If you want a y equals mx plus b it, that's fine too. Either one are equivalent. Either one are okay. Neither one's any better than the other. I would actually argue on this one, potentially easier to use the y equals mx plus b format to solve this thing, because they're asking that we approximate f of 0.2 using the linearization. So what they want us to do here is take and say, well, what's f of 0.2? So that's going to be, let's see, f of 0.2 is approximately 2 times 0.2 plus 1. So again, this is an approximate. This little wavy equal sign means approximate. They're asking us to approximate f of 0.2. We have a tangent line that touches the graph at one spot, specifically at 0, 1. And then we're using that tangent line to say what the function would be close to being worth at 0.2. And plugging that in, 2 times 0.2, we'd have, what would that be, 0.4 plus 1, and so our approximate would be 1.4. So we could say f of 0.2 is approximately equal to 1.4. So that answers part B. And then part C, and this is the heavy point-intensive piece, and in this particular year, I think it's actually worth 6 points. We're going to work through the separable differential. So equation to the tangent line, not a big deal. Putting in a curve, not a huge deal. The bigger deal, or the more challenging piece, is going to come on part C. So finding that particular solution and using that initial condition. So let's start with our dy over dx, and that's equal to 3 minus y times the cosine of x. This is a separable, so we're going to separate it. I'm going to multiply both sides by dx. And again, you're welcome to do this part in one step. I'm going to do it in 2. I'm going to divide by 3 minus y, and I'm going to write that as 1 over 3 minus y. And I've got my x's on the right-hand side, and I've got my y's on the left. And from here now I can integrate. So I'm going to integrate both sides. And on the left-hand side, I'm going to have to be a little bit careful because I see that negative y, and that's going to impact the u substitution. So we'll come back to that issue in a moment. And on the right-hand side, I've got cosine of x. So if I integrate that thing, the integral of cosine is sine. So I'm going to start with the piece that I know I can get without a lot of hassle. And then I've got my plus c. And again, what we're going to do is look to incorporate that 0, 1 initial condition to get plus c. But to do that, I need a left-hand side. Technically speaking, what you have going on that left-hand side, and I'll just maybe, let's see, because we have all these wonderful colors, let's use a new one. We're integrating 1 over 3 minus y. You are here using a u substitution of u equals 3 minus y, which means du equals negative dy, or negative du equals dy. So we've got negative 1 over u du, and that's going to be negative ln of u, and then u is 3 minus y. That's the thing that's happening over on the left-hand side. If you are comfortable not doing the u substitution and just making the jump straight to here, you just have to be really, really careful that that negative sign shows up, but you'd be okay, and the AP is actually all right with that. That being said, if you want to be careful on it and do the u substitution, there's no harm in that either. So we've got negative ln 3 minus y. And again, the plus c just shows up on the right. Now what we need to do is actually find c. So I'm going to take my 1 and I'm going to plug it in for, and actually what I've been doing red on this step. So I'm going to take my 1 and I'm going to plug it in for y. And I'm going to take my 0 and plug it in for x. I'm going to figure out what c is. Sine of 0, that's nice, that's 0. So I get c all by itself. And then, let's see, this would be negative ln. 3 minus 1 is 2, so the absolute value bars, not really necessary. And ln of 2, we don't need to know what that is. We're just going to express it as ln of 2. We need to know it's a number, but other than that, we don't need to do anything with it. So then I'm going to take, and I'll go back to my black pen to indicate we're continuing to plow through this thing. I'm going to swap c out. And I've got this expression. I now need to isolate y. And to do that, I can knock the negative sign off there right away. So I can just say, okay, let's go put a negative over on this side. And I'm going to do that thing where we do the little switching of putting the positive term first. Not a huge deal if you do it or don't do it, but for me it just helps. So we're gonna go with that. I'm going to e both sides to get rid of the ln's. So I'm going to e both sides, or e to the both sides. And that gets a little tricky on the right. On the left, e and the ln drop, and I've got 3 minus y. And then we got to figure out what to do with this right-hand side. So if I've got e of two things being subtracted, another way to think about that is e to the ln of 2 divided by e to the sine of x. Because when you have the same base, both two things raised e raised to two different things, or the same base raised to two different powers. When you divide those powers, it's like you're subtracting, or when you divide the expressions, it's like you're subtracting the powers. And so we could write the expression like this, and then e ln of 2 just is 2. So I've got 2 over e to the sine of x. Now, and here comes the challenging part, or, well, if this wasn't challenging up to here comes the challenging part. 3 minus y, we got to deal with that. So to deal with the 3 minus y, to isolate y, which is the last step, we have to think about this side of things. So the question becomes, can we drop the absolute value bars? In order to isolate y, we're going to have to do that. And that's where, when we scroll back up, we're going to use this equilibrium solution piece. So we're going to use this band of zero slopes. And again, just to highlight that, up here, we've got a band of zero slopes. What that means is, if we start with an initial condition, and we did, that is below that band, we are not going to punch through it, because as you get closer and closer to it, you're eventually going to flatten out. And maybe you get all the way there, you'll touch it, but then you'll drop back down, or you get really close to it and drop back down. What that means is our function's y values are all going to be trapped below 3. We're not at any point in time going to rise up above 3 for y values. Where that comes into play is when we go back down here. If we know y is, and I'll do a little aside here, if we know y is always below 3, then the expression in absolute value of 3 minus y is always going to be positive. It has to be. If y values can't be bigger than 3, that expression on the inside can't be negative. Therefore, we are allowed to, or we can just drop the absolute value bars. And I would say, if you get to an AP question and they put this kind of wrinkle in there, if you're not tracking 100% with what I'm saying about the absolute value bars, by default, just think, when I get to this stage, I'm just going to drop the absolute value bars. That being said, that shouldn't be your mode of operating, but just if you are in the testing environment and you're uncertain, the bulk of the time you can drop them. There are a rare number of cases where you cannot, and you just leave it as absolute value bars, but you want to go back to the initial condition. You want to look at the slope field and figure out what's true about those values. And again, that involves a lot of abstract thought and kind of tangential thought on this one. But we can drop the absolute value bars, which means I can subtract a 3 from both sides. And then I can divide by a -1. So I'm going to get y equals, I'm going to do that little switch again, 2 over e to the sine of x. And that then is a y equals expression. You can certainly combine those two into one expression. You do not have to, but that is our final piece, our y equals expression. So we've wrapped up the problem. Certainly, if you want to write this thing some other way, you can. I believe the scoring guide expresses it. Let's go y equals 2e to the negative sine of x. Just an alternative way to write the expression. Both would count, both would be fine. You've shown you know what you're doing on this particular problem. So again, walking it back through, we have to separate things. So that's what we were doing in these first couple of steps. So let's see, we've got our y's and x's together here. So check, we've separated. Next, we had to integrate. Check, we integrated. Next, we had to get our plus c. Boom, got it. Then we had to solve for c. That's this piece in red. Then we have to isolate y, and that's the rest of it. So this big chunk of stuff that we did to get all the way to the bottom is the isolating of y. It's the same set of steps. This one just involved a few more hoops, and it asks us to think about what's happening within the absolute value bars, which again is kind of this challenging, abstract, tangential thought, but this is a good problem to highlight that. So hopefully it helps. What I would like you to do is try the other problem on the worksheet page and then check your solution against what's printed. It's another slight wrinkle on differential equations.